This is the next video that we're going to be doing in this series, all the equations that you need for your chemistry exam. This time we're going to be doing the specific heat equation as shown here. This technically, I guess, isn't chemistry, it's physics, but it is pretty central to thermochemistry. So here we have the version that's given in NCEA, and you'll notice that it's exactly the same as the Australian exams will give you, the HSC and Victorian certificate, etc. Even the font is the same. This is the version that you'll be given in the International Baccalaureate, the IB exam. Notice the only difference here is the big Q, whereas the others have the little q. They mean the same thing. So not given is another formula which is pretty useful, which is Q equals ML, capital L. And we'll be looking at that one in a second as well. So first up, let's have a look at what these variables actually mean. So Q, I'm going to call this lowercase q. So let's look at what these variables actually are. So Q here is energy, and it's the energy provided or required or lost to or from a substance when we heat it. So when it gains temperature or loses temperature. So this is energy, so it's the unit for this is going to be joules, J, or some unit of joules like kilojoules. You might even get megajoules, something like that. The joules and kilojoules are the most commonly used. Kilojoule is 1,000 joules. Okay. Mass, M is mass, and this is going to be in either grams or kilograms. So note this is the absolute mass, this is not the molar mass. So this is the size of the substance that's been either cooled or heated up. C. Now C is the big one here. This is the specific heat capacity of a substance in a specific state. So we can define this as the amount of energy required. Well, the amount, let's say the amount of thermal energy required to heat or cool a substance, usually 1 kilogram or 1 gram, by 1 degrees Celsius or 1 degrees Kelvin. Remember, 1 degrees Celsius and 1 degrees Kelvin are on the same scale. They have a different starting point, but they're on the same scale. Okay, this is specific, as the name kind of implies, to each energy. So different elements, different substances have different specific heat capacities. Metals tend to have a very, very low specific heat capacity. They're quite good at conducting and heating up very quickly. If something has very, very high heat capacity, it means you have to put in a lot of energy to heat it up. Okay, the delta T. So it's delta capital T as opposed to delta little t, which would be change in time. This is change in temperature. So the delta just means change in. And this is going to be, we could even do this a bit more specifically. This is going to be the final temperature minus the initial temperature. And this is always going to be in either degrees Celsius or in degrees Kelvin. So there is a little caveat here, a little kind of star that we need to sort of note, provided that there's no state change. So in other words, if something goes from a solid to a liquid or from a liquid to a gas, all the heat is transferred. So this is a big presumption. So what we're going to be presuming essentially is that if we have, say, a container with some liquid and we apply some heat energy into it, that all of that heat energy is going to go into the liquid. In reality, and especially in conditions outside the lab, that's definitely not true. So there is a thing called entropy, capital S, and it can be represented by change in entropy. And this really, we can sort of define this as kind of like lost energy, really, from our system. You can't create or destroy energy, but it can lose its usefulness in the form of entropy. There's no perfect reaction. There's no perfect way of doing things that's going to produce 100% yield of anything. But for our purposes, we're going to presume that everything we do is perfect. The best way to investigate things or to do them is to do actual examples. So let's do a few. So we're asked to calculate the heat energy required, so that's going to be Q, to raise the temperature, so therefore change in temperature is going to be positive, of 150 grams of water. So mass is going to be 150 grams from 20 degrees to 55 degrees. So that's going to be our change in temperature. And we're given explicitly that the specific heat capacity is 4.18. Now, notice the units, it's joules per gram degree Celsius. So this is already in grams, which means our answer is going to need to be in joules. All right, let's do it to it. So Q is MC, change in temperature. The mass is given as 150 grams, and it's already in the units. The heat capacity is already in the units that we want, 4.18. And the change in temperature is going to be the final temperature, 55 minus 20, so 35 degrees. So 150 times 4.18 times 35, positive 35. Okay, and we grab Mr. Casio and let him do his thing. So 150 times 4.18 times 35 is 21945. So 21945. What's the unit? It's going to be in joules. So if we were to sort of round this, we could say it's 21.945 kilojoules if we wanted to do that. We could say it's approximately 22 kilojoules if we really wanted to round it, but I'd probably leave it as joules. They give the question to us in joules and grams, so it's reasonable to expect that the answer that they want would be in joules. So a similar question, but kind of backwards. A 50-gram block of copper, so that's little m, and it's in grams. So when you go through these, note what the variable and the unit. Cools down from 100 degrees to 25 degrees Celsius. So the change in temperature is going to be negative. So it's going to be 25 minus 100, which is negative 75 degrees Celsius. They give it to us in degrees Celsius, which is good. How much energy was released? And they quite helpfully here give us the specific heat capacity of copper. Notice that it's a lot lower than water, so it's a lot easier to heat up a metal. So it's 0.385 joules, which is good, per grams, which is what we've got, degrees Celsius, which is what we've got. So the answer is probably going to be in joules. So let's just do the maths. Okay, the mass is 50 grams. The specific heat capacity is given here. And the change in temperature, we already worked it out, is minus 75. Right, grab your calculator and get the answer. So 50 times 0.385 times negative 75 is negative 1443.75. So the negative denotes that this is an exothermic, not reaction, but it's an exothermic process, and the copper loses this amount of energy. So it loses 1443.75 joules. We could say loses. Okay, so we in an exam you would need to sort of state that you would need to state the direction of where the energy is going to. So in a wording question, why does sanded beach feel very hot on a sunny day, while the ocean water feels cool, even though both receive the same amount of sunlight? So in other words, the amount of sunlight, so the Q that both receive is the same. What is different? Well, the specific heat capacity of water, is it water? Yeah, it's water, is much, much higher than the specific heat capacity of the sand, which I think is silica base, and there's other stuff in there as well. And that's that. So when we have a mass of water, the mass of the water and the change of the temperature is going to need to be much, much lower if the Q is the same. I think maybe I'll explain this a bit better. So let's say that the specific heat capacity of water is 2 kilojoules per kilogram, and the specific heat capacity of the sand is 1 kilojoule per kilogram per degree Celsius. Okay, and there are Q is 20 joules. Okay, if we look at the water first, so 20 is going to be equal to the mass of the sand, and we'll say we've got 1 kilogram of each, is 1 kilogram times 2 kilojoules per kilogram times the change in temperature. What's the change in temperature going to be? Well, the change in temperature is going to be 20 divided by 2, which is 10 degrees. So the water is going to increase in temperature by 10 degrees. If we look at the sand, however, so the same amount of energy goes into it, and there is 1 kilogram, but the specific heat capacity of the sand is 1 times the change in temperature. If we solve this for change in temperature, the change in temperature here of the sand, I see the change in temperature of the water, is going to be 20 degrees Celsius. So for the same amount of energy going into the substances, the change in temperature is markedly different. So now we're told that a 200 gram sample of an unknown liquid, so the mass is 200 and it's given to us in grams, is 4,000, it absorbs 4,000 So 8,400 joules of energy. So Q is 8400 joules, and raises the temperature by 10 degrees Celsius. So change in temperature is positive 10 degrees. What is the specific heat capacity of the liquid? Okay, so Q equals MC, change in temperature, and now it's an algebra question. So we know that the Q is 8,400. It's going to be equal to 200 grams, and it's all in the same units, times the specific heat capacity, and we don't know what the specific heat capacity is, but we're trying to find it, times the change in temperature, which is 10. So 8,400 must be equal to 200 times 10, 2,000 C, and now we're solving for C. So we're going to divide both sides by 2,000. So C is going to be 8,400 divided by 2,000. And I'm not sure what that would be on the top of my head. It's going to be 3 point something. 4.2. Okay. Oh, okay, so yeah, 4.2. So the specific heat capacity is going to be 4.2. And what's the unit going to be? It's going to be joules per gram degrees Celsius. So note there, we could use this as a really useful way of identifying a substance if we didn't know what it was. We could look at it and test to see how much the temperature changes if we put an amount of heat energy into that substance. It would be really blunt, I imagine, but it's there. Well, let's have a look at another related formula, and this is the formula Q equals mL, where L is the latent heat capacity of a substance. And this is we're going to define this as the energy required to change the state of a substance. Okay, so notice something which is missing in this equation is the change in temperature. This is missing. And the reason being is that when something changes state, it stays the same temperature. It reaches a critical temperature where it can change its state. But once it reaches that temperature, it needs extra energy. It either to take in extra energy if it wants to go from a liquid to a gas, or from a solid to a liquid, or to give out energy if it wants to move from a gas to a liquid, or from a liquid to a solid. I know there are other ones there, but we're going to presume for our purposes that we can go from a solid to liquid to gas. Okay. The latent energies are not going to be the same. So the energy required to change something from a solid to a liquid is not going to be the same as the energy required to change it from a liquid to a gas. Okay, but we're going to presume that the energy that it loses when it goes from a gas to a liquid is the same, but in reverse of the energy going into it when it becomes a gas from being a liquid, if that makes any sense. Okay, so if, for example, we have a solid piece of ice, okay, and it's at -4 degrees Celsius, and we're going to presume that it's at sea level. Okay, so the pressure is standard pressure, and we want to convert this into liquid. First thing we have to do is heat it up. So we have to put in thermal energy to take it to 0 degrees Celsius. Okay. Now it's not going to just magically boom, instantly become water. we're going to need to keep putting some energy into it, and then it's going to become a liquid. So the energy to get from here to here is ml, the mass of that liquid times the latent heat capacity of that liquid. And also, if we have liquid and we want to turn it into gas, representing gas by the sort of the molecules kind of floating around in a container here, we're going to need to, and this is water, we need to bring it to 100 degrees Celsius, and it's going to stay 100 degrees Celsius. It's not going to convert into a gas unless we put specific heat into that in order for it to become a gas. Okay, going backwards, if we have the gas here and we want to convert that into a liquid again, it needs to give off the same amount of heat energy in order to become a liquid, as we already worked out here. So these are going to be the same, they're the same process, but in reverse. And I might actually just post a previous video that I did on this with some examples.
Hello and welcome. Today we are going on a really cool journey of transformation. Seriously, we're going to take a simple block of ice and figure out exactly what it takes in terms of physics to turn it all the way into super hot steam. All right, let's dive right in. So let's just start with the big question. You toss a block of ice in a pot, you turn on the stove. What's really happening on a molecular level? How much energy does it actually take to push it from a solid to a liquid and then all the way to a gas? It's definitely more complex than you might think, but hey, we're going to break it all down. Okay, so the very first thing you've got to get is that there isn't just one thing happening here. There are two totally different jobs that the energy has to do. One job is making the substance hotter, and the other, completely different job, is to change its form. And for two different jobs, you're going to need two different tools. Think of it like this. The first kind of energy just makes the water molecules dance faster and faster and faster, and that's what we see as a temperature increase on a thermometer. But the second kind of energy, it doesn't speed them up at all. Nope. Instead, it works like a key, unlocking the actual bonds that hold all those molecules together. It lets them go from that rigid solid ice to a flowing liquid, or from a liquid to a gas just floating around. So let's check out our first tool. This is the equation we pull out of our physics toolkit anytime we see a thermometer is reading actually going up or down. This one is all about changing the temperature. And here it is, E equals mcΔT. This is called the specific heat equation, and it is our go-to for figuring out the energy needed to change something's temperature while it's staying in the same state. Let's break this down. E is the thermal energy we're adding, measured in joules. M is the mass in kilograms, pretty straightforward. Delta T is just the change in temperature. But C, the specific heat capacity, now that's the really interesting part. It's kind of like a personality trait for a substance. It tells you how much energy it takes to raise just 1 kilogram of it by 1 single degree Celsius. So here's the crucial physics point. When you use this equation, E equals mcΔT, all that energy you're putting in is going into one thing, increasing the kinetic energy of the molecules. You're just making them wiggle and jiggle and move faster. You're not breaking any of the bonds between them. Not yet, anyway. Now, take a look at some of these values for C, the specific heat capacity. Check out water. Its value is a whopping 4,186 joules per kilogram per degree Celsius. Now compare that to something like copper, which is way down at 385. This means water needs over 10 times more energy to heat up than copper does. This super high specific heat is why oceans can absorb so much heat from the sun, and, why it feels like it takes forever to boil a pot of water for pasta. Okay, let's make this real with an example. Say we want to heat 2 kilograms of water from a cool 20 degrees up to its boiling point at 100 degrees. We just plug the numbers in. The mass is 2, we'll use a rounded value for C of 4,200, and the temperature change is 80 degrees. You multiply them all together, and bam, you get 672,000 joules. That is a lot of energy just to get the water hot. All right, let's move on to our second tool. This is the one we use for those really weird moments when you're pumping tons of heat into something, but the thermometer, it doesn't move one bit. This is our breaking the handcuffs tool, the one we use for a phase change. And the equation is just beautiful and simple. E equals m times L. This is the latent heat equation. So again, E is energy and m is mass. But L stands for specific latent heat. Now the word latent literally means hidden, and that's the perfect way to describe this. This is the hidden energy you have to pump in just to break those molecular bonds and change the state, all while the temperature stays completely, totally constant. This just nails the whole concept, right? Your ice is melting, it's obviously absorbing heat from the stove, but a thermometer sitting in that icy water is just gonna sit there reading 0 degrees Celsius until the very last sliver of ice is gone. All that energy is busy breaking bonds, not raising the temperature. And just like C, L is a specific property, but there are two main types you'll see. There's the latent heat of fusion, that's LF, which is for melting or freezing. And then there's the latent heat of vaporization, LV, for boiling or condensing. And just look at the difference for water. It takes 334,000 joules to melt a kilogram of ice, but it takes a staggering 2,260,000 joules to boil that same kilogram of water into steam. That massive amount of energy is exactly why a steam burn is so much worse than a burn from hot water. So let's go back to our 2 kilograms of ice at 0 degrees and calculate the energy to melt it. It's just mass times the latent heat of fusion. So 2 times 334,000, which gives us 668,000 joules. Get this, that's almost as much energy as it took to heat the water by 80 degrees, but in this case, the temperature didn't budge at all. Wild. All right, time for the main event. We have our two tools. Let's put them together and map out the entire journey, from a block of ice below freezing all the way up to steam that's above boiling. It's a 5-step process. This heating curve you're looking at, this is our roadmap. It's super important. Whenever you see the line sloping upwards, that means the temperature is changing, and we use our first tool, E equals mcΔT. But whenever you see a flat plateau, that means the state is changing at a constant temperature, and that's when we pull out our second tool, E equals ml. So this breaks our entire journey into 5 clean stages. Step 1, heating the solid ice up to 0. That's a slope, so we use E equals mcΔT. Step 2, melting the ice. That's our first plateau, so we use E equals ml. Step 3, heating the liquid water. Another slope, so we're back to E equals mcΔT. Step 4, boiling the water into steam. That's the long plateau, so it's E equals ml again. And finally, step 5, heating up the steam itself. That's our last slope, so it's back to our old friend E equals mcΔT. So let's look at a quick 2-step example right here. Let's say we want to take a small ice cube, maybe 35 grams, from 0 degrees solid to 5 degrees liquid. Well, step 1 is melting it. We use E equals ml, which takes 11,550 joules. Step 2 is heating that newly melted water from 0 to 5 degrees using E equals mcΔT, which takes another 735 joules. The total energy, you just add the 2 steps together, 12,285 joules. That's it. Okay, let's wrap this all up with a really clear summary of your physics toolkit. And, of course, some pro tips to make sure you absolutely nail these problems every single time. Here it is, the absolute golden rule. Before you even write down a single number, ask yourself one question. In this part of the problem, is the temperature changing or is the state changing? If the temperature is changing, you use E equals mcΔT. If the state is changing, you use E equals ml. That's it. They never happen at the same time. It really is that simple. And finally, let's avoid the easy mistakes. First, please always convert your grams to kilograms. The formulas demand it. Second, double check that you're using the right L value. LF for melting, LV for boiling. Third, never ever try to use E equals mcΔT for a phase change, because the change in temperature is 0 and the formula just won't work. And last, for those multi-step journeys, don't forget to add up the energy from every single step to get your final answer. So now you have all the tools to calculate the total energy needed for any phase change journey. But here's a final thought to chew on. Knowing the energy doesn't actually tell you how fast it's all going to happen. I mean,
A tiny candle flame and a giant jet engine could both deliver the same amount of energy, just over very, very different timescales. That question, how quickly energy is delivered, well, that's a question of power, and that is a topic for another day.
So let's get to thermal energy. So Oliver wants to keep his water cool the whole day while he's at school. Why he needs to do that is beyond me. I'm just going to turn off the speaker. Turn off that speaker. The whole day while he's at school, I mean, he could just use the fountain that just keeps it cool. Firstly, he tries freezing the water to take to school. Over the day, Oliver finds it takes a long time for the ice to melt. Once the ice has melted, the water gets to room temperature quite quickly. I cover this topic really, really thoroughly in a previous video a couple ago. I think it's Heat Energy Explained or something like that. But before we do that, a good practice when we in an exam is to look at what they're giving you and sort of apportion what is the letter that goes with this. Well, the specific heat capacity of water is little c. Is it in SI units? Yeah, it is. It's in joules per kilogram. The latent heat of fusion is this huge number here. What letter is that? Well, that's big L. Is it in SI units? Yes, it is. It's in joules per kilogram. Mass of the water is 750 kilograms, 0.750 kilograms, so that's little m. This one here, volume, it's not given in any of the formula, and I suspect it might just be a red herring. Okay, what does the term latent heat of fusion? So this is represented by this little formula here, ml. So this is the thermal energy required to transform 1 kilogram of substance, in this case water, from ice to liquid and vice versa. Okay, so if we have a 1 kilogram block of ice, we need to put this huge number here into it to transform it into water. And conversely, if we have 1 kilogram of liquid water, we need to take this amount of energy off to transform it into ice. It won't just, do it all by itself for any reason. All right, so now it wants us to calculate the heat energy required to change the state from solid to liquid. So we're going to use the formula that they give us, the correct one. Do not use that one. That's for heating the water up. This is for transforming it. So the mass is given as 0.750 kilograms. It's already in SI units, so do not use the volume for this. We use the mass, and the L was given as this huge number here times, I've got the formula sheet in front of me, so I'm just using that. Okay, well, now it's just a matter of grabbing our good old calculator. Let's clear all of that. 0.750, but I mean, it does matter, times this huge number, 250,500 joules. Remember, you always need the units. Probably more likely you would say 250.5 kilojoules, to be honest, which is a lot of energy. That's why it takes so long to thaw that ice out. And if you notice here, the latent heat of fusion is way, way greater than the specific heat. So it takes several times more energy to thaw the water than to heat the water, which I suspect might be the next question. And it is the next question. The temperature against time graph below shows what happens to ice when ice is taken out of the freezer. So use the information provided opposite and the graph below to describe the reason why it takes a longer time for the heat to turn from the water to turn from ice to water, essentially. So on this axis here, we have the time. So it's going to be in there, and this is going to be the thermal energy. All right, so here it heats up fairly quickly here, and in here it is going to be the MC change in temperature. So this is specific heat that's working here. Then when it reaches freezing point, 0 degrees Celsius, now it's latent heat that's doing all of the work. The latent heat is way bigger than the specific heat, so we need lots more of it from the outside air before it can melt. And then as soon as it's melted, the latent heat is irrelevant, really, and then it just keeps going up. And if you notice the slope here, the slope here is going to be the same as the slope here. And that would be the answer to that one. So some variation of what I said there. All right, the next question is Oliver now decides he wants to use a thermos flask that holds the same volume of water. Okay, so that's important. So we know that the volume is the same, therefore the mass is the same. So the mass is known. The thermos flask is known as a vacuum flask. Good. The double-sided glass vessel that is designed to minimize heat transfer by keeping hot things hot and cold things cold. In case you did not know how a thermos flask works, describe 2 features of the thermos that reduce heat transfer. I'm going to actually do 3. So there are 3 ways that heat transfer can be minimized, and they all appear in here. So the first one is conduction. So conduction is when heat moves through solid. Okay, so the glass itself is a poor conductor. Okay, describe 2 features. The other thing which is a poor conductor is the stopper. So the stopper is probably made of some sort of rubber-based something, I guess, which is also a bad heat conductor, or a poor heat conductor. All right, the next way that heat can be transferred is by convection. So here, the vacuum itself, vacuum itself is a poor conductor, is a poor medium for transfer of heat. Okay, so heat doesn't travel across a vacuum because there are no particles to interact, and there's no kinetic energy transfer. So I do a bit on that on my previous video. The other way, which probably not a lot of students did, was radiation. So the glass is shiny, so there's a reflective coating. The reflective coating here, and that's going to reflect thermal energy. The reflective coating will reflect thermal radiation. Radiation is, of course, transfer of heat energy through electromagnetic waves, and that's going to reflect this. It's the reason why those space blankets are effective. They reflect radiation of heat. Next question says that Oliver decides to test this thermos and finds that at the start of the day, the temperature of the water is 5 degrees Celsius, and 5 hours later, it's risen to 12 degrees Celsius. Showed that the average rate of thermal energy absorption of the water in the thermos over the 5 hours is approximately 1.2 watts. All right, first thing we need to do is we need to work out what our variables are. So we're going to use the formula change of energy. The thermal energy is going to be MC, change in temperature. We're going to presume that it's at sea level, so it doesn't need to change states from ice to liquid water. So the latent heat energy isn't involved. It's the specific heat capacity that's involved. The mass, we know what the mass is. So the mass is, 0.750 kg. We know that the specific heat capacity is given as 4,000 joules per kilogram, and the change in temperature, remember we don't really care which direction it's going, we're going to use the same amount of energy, is going to be 12 minus 5, so it's going to be 7 degrees Celsius. Okay, so we can now work out how many joules of energy goes into this water in the thermos flask to change its temperature, and for that we're going to just grab our calculator. So our mass is 0.75 times 4,200, let's move this calculator across, times the change in temperature, which is 7 degrees, and we come up with 22,050 joules. Quite a bit. Okay, now we know the energy, we need to work out the power. And for that, we're going to use the formula that's given in the formula sheet. The change of energy is going to be equal to the power times the time. I've noticed last year they changed T. The year before that it was change in T, but now it's just time. So that's good. We know this. This is going to be this. The time, we kind of know this. We have to always ask ourselves, is it in SI units? And the SI unit for time is not hours, it's seconds. So we have to work out how many seconds there are in 5 hours. So 5 hours times 60 minutes times 60 seconds. So there are 18,000 seconds in 5 hours. So T equals 18,000. And now we have enough information to find the power. So let's just do the algebra first before we put the numbers in. So we're going to divide both sides by T. They're going to cancel. So the power, the average power, is going to be the change in energy divided by the time it takes. And that's going to be 22,050 joules divided by 18,000 seconds. And now we can put it in the calculator. So 22050 divided by 18,000 is 1.225. So comparing that is that, and that's going to be watts. So comparing that's going to be equal to 1.2 watts at one decimal place, or two significant figures. So yeah, it is. So a tiny little bit of energy gets through this kind of fortress of thermodynamic walls here. And I think that's the end of that question.